Thanks everyone. I guess, so my name's Stefan. I kind of lead the model lifecycle team on data platform at Stitchfix for the last 6 years. And I'm going to, present to you about Hamilton, which is a little Python micro framework we open sourced in October last year. And it came out of, helping a team of data scientists get their work done. So what to keep in mind for the next 40 minutes or so. Hopefully I'm speaking slow enough such that you can all understand me. Do call me out if I'm speaking too fast. That's the one thing that I end up doing sometimes out of habit. But essentially for the next 40 minutes, I'm going to try to talk to you and explain to you what Hamilton is, and that it's a new paradigm to create data frames. But just I'm going to kind of anchor the talk around pandas data frames, but just keep in the back of your mind that Hamilton actually can operate over, NumPy matrix, create NumPy matrices, can create, scikit-learn models, like any Python object you can kind of model with Hamilton. But for this talk, I'm kind of going to anchor it around pandas data frames. That Hamilton was a productivity boost for the teams at Stitchfix who used it. And as Bill said, this is an open source project. You can go look at all the code on GitHub. We also have a Discord community if you're interested in joining as well. So first I'm going to, talk about the backstory, then talk about what Hamilton is, how it was used at Stitchfix, and then what you can do with it, and then some a future roadmap kind of as to like where we think Hamilton can go. So at Stitchfix, there was a data science team called the Forecasting, Estimation, and Demand team, or FED team for short. And they're responsible for creating operational forecasts that the business makes decisions on. So for instance, how many people should we staff in our warehouses given the demand of our services? And it's one of the oldest teams at Stitchfix. Their essential basic workflow is their basic workflow is sorry, I don't think I clicked the button. Anyway, hopefully anyone can hear me. But essentially the Feds team's workflow looks something like the following. They get actual kind of business data. They then create a data frame, so featureize it. They then fit some models, predict the future, and then output a data frame that with a forecast that the business makes decisions with. But one thing that was happening was that this process was on fire for them, and due to the operational nature of their role, they were kind of pretty stressed. And so what ended up happening was my team came in. It was that their biggest problem was actually in managing and featureizing the data frame, and this is what Hamilton helped solve. Why was this data frame, causing them issues? Well, here's a kind of sketch of what it looks like. So the point is that there aren't that many rows. There aren't millions of rows. It's the order of tens of thousands of rows. But the data frame is on the order of thousands of columns wide. The point here is that it's not big data and it fits in memory. In the way that at least for those who aren't familiar with time series forecasting, with kind of feature engineering for time series forecasting, you essentially are going to be creating lots of columns that are kind of functions of other columns. So here I'm just showing that if you wanted to create a Boolean indicator that some week was a holiday, you would put in year and week to generate it. And so what generally happens is that you then end up creating this chain of dependencies to create other columns. And so columns are functions of other columns, and essentially the code and the way that they were writing it was really what was causing them pain. Why? Well, let's look at some code as to why was this code starting to get painful for them. So here I have some pandas code where you're loading some data, manipulating a data frame, adding some columns to it, and there's like several ways you could do it. Maybe you're passing the data frame to a function and then returning, say, a column there and then assigning it. There's this code looks pretty simple. Doesn't look too looks pretty innocuous. I think with the challenge that this team was facing was that, okay, scale this type of code to thousands of columns and also a growing team, so people coming in and out, you're going to have a bunch of problems. So why? So specifically, this code results in a lot of heterogeneity. So there's a lot of different ways that you can create a column and attach it to this kind of central data frame. You have these inline data frame manipulations, which are, these one-liners that look nice and great. You can write the code really quickly, but, how do you document it? How do you unit test it? And then, through the script, code ordering becomes super important. So if you don't know the dependencies of how, which depends on what, it's very easy for you to kind of screw things up. And then you have to you end up generally managing a monolithic script that you use for all your use cases. And so it becomes, it has a lot of stuff in it, which maybe it doesn't need to. So specifically, unit testing is difficult. Documentation, is hard. This impacts code reviews because our code reviews, are more challenging. And then this impacts as the code base grew, onboarding becomes more difficult and debugging because you really need to understand the code base and like how everything kind of interconnects for you to really kind of make sense of things. In short, the code for the featureization was causing this team issues. And so we came up with Hamilton to kind of fix that. So at a high level, Hamilton is you write some code in this kind of specific way as a user. You then pass it to Hamilton. Hamilton then can construct a directed acyclic graph or a DAG. So that way we can kind of know what needs to be called before what to kind of create the right outputs. And then you as a user then tell Hamilton, hey, create an object for me. And in this case, it would be, a data frame. Yeah. So that's that at a high level. You write some code in a special way, provide it to the Hamilton kind of library code to create a DAG from it, and then you use that, tell Hamilton then with that to kind of create the specific kind of output you want. And when I said it was, this is a new paradigm. So you, rather than writing functions like I showed you before in a script, you write these declarative functions. So what I mean by declarative is that the function name kind of declares the output and the function inputs declare the dependencies or what inputs are required to compute things. So here I have, a simple line of code that says create column C by summing column A and column B. In Hamilton, you would kind of rewrite that into a function where, column C is the function name, and then the inputs, arguments to the function are, the other columns or inputs that are required to compute things. So in this case, it'd be column A and column B. You then have, we can add some type hinting to help with, code readability. And then, oh, look, there's a nice spot for documentation. So everything is, you can document things pretty easily. And then, the body of the function then is all about logic. You essentially build up this kind of, these sets of functions. And then from there to build a directed acyclic graph, what we do is we just kind of, use the Python inspect module. We extract, the function names and parameters. And then from there, we kind of connect everything and we can build a DAG. And this is, using graph theory 101 to do so. So nothing too complex here. So once we have this DAG, this representation, like you then as a user provide, inputs and outputs, and then Hamilton walks the right, with those two things in mind, walks the DAG to figure out what needs to be computed, determines the execution path, and then functions are only executed once, and then right at the end is when everything is kind of combined. So key point to remember with this paradigm, if you think when I'm talking about Hamilton, is that Hamilton requires the function names and function parameter names to match between functions so that we can stitch together this acyclic graph. So the names that you put here are meaningful and help construct the DAG. And so therefore the functions, then it's really easy to read the function because they then declare what their output is and then what their inputs are. Second key point to remember is that as a Hamilton user, you do not have to maintain. You kind of model this. You write these functions that model this kind of create this DAG, but you don't need to kind of maintain how everything is connected with each other, since Hamilton takes care of that for you. So you don't have to maintain this monolithic script of how everything connects because you've already kind of encoded that in the functions. And so this is good. So this means, there's a lot less upkeep and maintenance for your feature engineering or your feature or data engineering, since, the functions declare what outputs and inputs they are. They know how they interconnect, in which case, like, you don't need to then maintain a central script somewhere that like does this. And so this is one burden that Hamilton helps resolve. In one sentence, if I was to kind of summarize Hamilton, it's a declarative data flow paradigm. And so declarative, as I was kind of explaining to you before with the functions, and data flow is because we're really mapping, how data and computation work together. You might be wondering, why do we call it Hamilton? Naming things is one of the hardest problems in computer science. So here I'll try to explain, how we came up with it. So as I said, this project started with a team called the Fed. And so connotations with the Fed, and this was a pretty foundational thing, is that the Fed also can, in the US, it can mean the Federal Reserve, in which case I was like, who created the Federal Reserve? It was Alexander Hamilton. And then also this Fed team at Stitchfix also models business mechanics. So in physics, there are kind of Hamiltonian concepts. And then we're also doing some graph theory here, and graph theory also has Hamiltonian kind of, named things. And so in which case I thought, Hamilton's a pretty appropriate name for this project. Okay, so hopefully at a high level, I've kind of explained what Hamilton is, but now I'm going to try to ground you with some code. As I said before with Hamilton, you kind of, you write functions that declare their inputs and kind of outputs. And so here I have, I've created, you curate your functions into Python modules. Here I have a module called myfunctions.py, and I have, 5 functions. Here I'm just showing you, like, the function names are the outputs, and then the inputs declaring what they require. So here with this last function, you can kind of see that, oh, look, it takes in spend shift 3 weeks. Oh, look, what is spend shift 3 weeks? Well, spend shift 3 weeks is defined here. You can then see, all these other functions taking the same inputs. So it's a kind of nice way to kind of figure out, dissect what requires what and how what's required to compute a particular column. So once you write this this module, you then need to write some sort of what we call driver code to actually get a result. So you need to actually tell Hamilton, okay, now you have these functions, I want to execute them. So you basically need to pass in some sort of dictionary of either, it's either configuration or maybe inputs or maybe both. You then need to construct or like import the module. Here, I'm just showing you can, programmatically import a module, but you could also just do import my functions, and that would, work here as well. We have an object in Hamilton called a driver object that then takes in this configuration and the Python modules that contain your Hamilton functions. After this step here, we then have built a DAG. And then from there, you just need to tell us, need to tell Hamilton, what outputs you want. You run the execute function telling it, hey, give me these particular columns. It outputs a data frame. And then also with Hamilton, we can also render what's actually being executed. So you can kind of visualize the process as well. In terms of implications for your code base, just to kind of hammer home this, what Hamilton causes or forces you to do is that functions are always in modules. So you end up having, curating modules, thematic modules, say, date features, date transforms versus numeric transforms, etc. And then you have, and the execution script is kind of decoupled from the functions. So in this code here, I haven't leaked at all really other than the module, like what the functions are. So this script is really kind of independent and decoupled from the transform functions. And so this is what I guess the point I'm trying to make across here is that you write modules and then you have separate these kind of driver scripts. And actually what this means is that it's really easy to reuse these modules in different contexts. And so you can actually have multiple driver scripts or multiple different kind of contexts of like that you can reuse the same definition. And so this is, I guess, one nice benefit of Hamilton over old ways of doing things. One thing to note for those, just not to confuse things, is Hamilton is not an orchestration system. So you might be thinking, oh, this seems similar to Airflow, Kubeflow pipelines, Prefect, Dagster, or Metaflow. Yes, kind of, but Hamilton isn't a system that you orchestrate things with. Instead, it's a system you model with, and so you would actually use Hamilton within a step of your workflow. So you would run it in a single Airflow step or a single kind of Metaflow step potentially, or in multiple. You can do that, and the reason why we call Hamilton a micro framework is because it's, it's embeddable. It's like small. You can put it, you embed it into Metaflow. You can embed it into Airflow, Kubeflow pipelines, and so that's just one thing to note. So Hamilton is open source. I wouldn't be, if you want to go ahead and try it, it's pretty quick and easy to install. The dependency footprint's pretty light. So pip install SF Hamilton should be able to get up and running. We do have some documentation and a bunch of examples in the repo if you're interested. So in short, Hamilton is a declarative data flow paradigm, whereas you as a user, you write these declarative functions that create a directed acyclic graph through the function name and function arguments. And then Hamilton handles kind of creating this DAG and executing things, and essentially enables you to kind of say bye-bye to these monolithic scripts. So with that, I'm going to switch to talking about Hamilton at Stitchfix. So it's been, you might wonder, so Hamilton's been running in production for over two years at Stitchfix, and it's been pretty successful for us. When we started, the original project goals were to improve. Is a question: is there a comparison of the number of lines of code that were required with and without Hamilton for doing the same task with data frames? So Hamilton, you could say, because it gets you to write things in functions, is a little more verbose, because you have one line for the function, one line for documentation, and then one line for the body. So in effect, you're essentially potentially, there's a 3-to-1 maybe, ratio of your code. The number of lines will increase, but that is to, you get a bunch of benefits, which I'll talk about in this next section. But essentially, yeah, Hamilton, you sacrifice being able to write things really concisely and easily, instead to make them always, readable and in a standardized and maintainable in a standardized way, which I'll kind of get into in this section, which I'll hopefully show you why that's important. So when we started Hamilton, project goals were to improve their ability to test, improve the documentation, improve the development workflow, and by rewriting things into this kind of function kind of paradigm, we got all of these, and actually I want to say we hit it out of the park. So why was this a home run? So testing and documentation, right? Because say with Hamilton, the function name maps to kind of an output that you can get, and it maps to exactly one function. There's a single place to find logic, so it's really easy to kind of search the code base and find things. And then there's only a single function that needs to be tested, and it just so happens that this function signature is beautiful for unit testing purposes, because you've declared what inputs are required. So it's really then easy to, in a unit test, to mock out the data that's required. So if you want to test your logic, like Hamilton functions are like 100% unit testable. And then it should be pretty understandable as to being able to read the function as to what it's doing, because the output names and the input names should largely mean something. And then because it's in a function, there's a natural place for documentation. So if you want documentation, you always have a spot for it, and it's always in a natural spot. So in short, by rewriting these functions, these transforms, everything is naturally unit testable, and everything is naturally documentation friendly. And so, as I said before, you pay a small price in terms of verbosity. Your total lines of code increases, but this is to help you maintain and test the code. And then so in terms of workflow improvements, so Hamilton also easily enabled, you can visualize your computation. So especially in time series, where some of these chains can get up to 20, 30 columns, kind of dependency chains deep, being able to visualize and understand it was very helpful. This decreased the time it took to debug things, and resulted in better onboarding and collaboration for the Fed team. And actually, as a bonus, they kind of built up this kind of central feature definition store, which I'll kind of touch on a bit. So visualization. So at Stitchfix, this team manages, a data frame with 4,000 plus columns. How do you, as a new person, figure out, heads or tails of it? Well, with Hamilton, you can, you can visualize it here. I've kind of, zoomed things out to obscure things, but you can kind of see that, once things gets pretty complex, having a visual means to look at it, is helpful. You can also export these as dot files, so you can put it into another visualization package if you wanted to. In terms of debugging, debugging functions with Hamilton is much easier, right? Because so there is only a single place where you can kind of define something. I mean, loosely speaking, in terms of a DAG execution, there's only one place that function can be defined. If there's a problem with that output, you just go to this one function to look at it. So either the problem is in the logic here, or it's in something upstream. And so it's also pretty easy to kind of read the function. And so if we wanted to debug this and it wasn't here, we would then recursively kind of walk backwards through the dependency chain to figure out what next should we kind of debug. And so debugging is pretty procedural. One nice thing about these functions being in modules is that you can also, import these modules into other contexts. So you could fire up your Python REPL, import this module, and then, play around with the function directly to kind of help debug, which, isn't easy to do if you previously just had a monolithic script, right? Collaborating on these functions is pretty easy. Why? Because, it's easier to assess impact and changes because, the names mean something. So if someone here was to say, update this span shift 3 weeks and change the number to 4, you'd see, oh, look, oh no, this isn't named the same. It's pretty clear that they should be matching. Maybe this should be, if I want to do span shift 4 weeks, I should create a new function, in which case it's very easy to add to and not touch this function, therefore not break anything that depends on it. So adding new inputs is really easy. Changing the names of things is really easy, just search and replace in the code base, and you've kind of covered all the cases. So yeah, changing the signature of a function is pretty easy as well, right? You just, oh, look, this needs a new thing. So when you're reviewing, like, why does it need this new thing? Okay, where is it going to come from? And then, yeah, it's easy to kind of figure that out. And the results in, code reviews that are much faster. Similarly, like you could delete stuff more easily with Hamilton because you could figure out, does anything depend on it? Okay, what depends on it? Is that needed? And so it's really easy to also, clean up code. And then if someone leaves your team, I would say with Hamilton, it's pretty easy to pick up where they left off because, just because Hamilton forces a naming of things, and documentation is really easy to kind of, and get you to chunk these functions. As you see, these functions are pretty simple, like, maintaining them is much simpler. So I see a question about anonymous Lambda functions. So yeah, Hamilton doesn't, no, it forces you to write these functions. So a Lambda function wouldn't make sense in Hamilton. You would have to, add it to a module if you wanted to expose it. I mean, you could do a Lambda function within a function, that's perfectly fine. But in terms of, the interface outside, that's how, a Lambda function, it wouldn't be anonymous, you'd have to name it, put it that way. So another question coming in. So what workflow tooling are you using together with Hamilton internally at Stitchfix? So at Stitchfix internally, we have Airflow, but that's kind of abstracted from data scientists. So, and this is modeled as like a Python task within that. So what are other tools to Hamilton that you considered before building this tool? So when we looked at this, there wasn't actually anything comparable. Right now, I still don't see anything comparable that takes this declarative approach and really, tries to separate materialization from using things. So here, as you can see, when you define these functions, you're not actually saying anywhere that you want this kind of, data frame materialized. You do that in the driver script, right? And so I don't see right now anyone who's taking that kind of approach. So, but I do, you could say PyTest has a similar approach in terms of declarative for like fixtures. That's probably one thing that's been, people have pointed out as something similar, but otherwise there isn't any tooling that as far as I know, that's similar to Hamilton. Maybe there's another open source package that kind of gets at it, but it's not implemented the same way as Hamilton. Cool. So So changing the existing modules can break the driver script. How is this prevented? So that is, something that, you need to, as a team, figure out. So if you are in your driver script declaring what outputs you want, you should, finding uses of a function, if you're going to delete or change, like that should be pretty, doable in your code base, right? So there is a bit of a human process aspect to it, but Hamilton, if you request something that isn't in the DAG, Hamilton will tell you, hey, it doesn't exist, right? So in which case, like, if that ever was the case, it's easy to figure it out. And then because the source of truth is code, and you're hopefully using Git, it should be pretty easy then to revert back, or version the modules so that things work. So you can there's a bunch of ways to kind of ensure that things are always running, and it really depends how you manage your Python modules and whether you make them version libraries or not, or whether you're using Git shards, etc. So good question. What about DVC? Only difference I see immediately is the auto discovery of functions. There you have to build your DAG. So DVC, as far as my understanding, is more about the data sets. So in Hamilton, it's not, we haven't exposed anything about data. We're just talking about code and data and transforms. And so I think they're kind of two separate tools. Now, DVC does get you, I think, has a Git-like kind of interface to data sets. I would say you can still use DVC with Hamilton. Hamilton will just, pull from that kind of data set. So, but I want to say there is, a lot of data tooling that does DAGs, because naturally that's a good way to model things. So there are a lot of things that, look similar, but actually I think are quite different. Is Hamilton compatible with Apache NiFi? I'm not sure what Apache NiFi is, but I'll look it up after the talk. Feel free to ping me afterwards. Okay, one of the results of using Hamilton was that the Fed team got a central feature definition store. So essentially, how this came out was that function names follow team convention. So for instance, D underscore is a prefix indicating, say, a date feature. So all their date kind of features have this kind of prefix. Their code is organized into thematic modules. So, all date features are together, all marketing features together, spend features are in separate modules. And then this allows them to kind of segment this larger DAG into sub DAGs for, like, iteration and purposes. And then it's all in a central repository, and it's versioned by Git. So then it's very easy to find and reuse features because it's a central place. You can then recreate features from different points in time easily. If you know Git, you can always go back and kind of, recreate something. In terms of testimonials, just in case you don't believe me, so Danielle said that she loves the encapsulation of the logic in a single named function, which makes adding nodes and edges simple to understand, communicate, and transfer knowledge. And so the impact of this is that pull requests are easier to review, and then onboarding new people to the team is easy. Shelley, also on the team, is she says, I like how easy breezy it is to add new nodes or edges to the DAG to support evolving business needs. So one of the cases at Stitchfix, marketing, hey, is coming up with a new push. They need to model it in their forecasts. So they need to add a new feature. This now takes minutes. It's just a matter of adding a simple function, not hours as it did previously. So question, so how do you parallelize these computations at Stitchfix? If so, how? So it really depends on your data size, whether parallelization makes sense. In the case of, we're on AWS, there's a large enough machine that fits all this data into memory. So in which case for the Fed team, parallelization wasn't that super important, since things can compute relatively quickly, in which case the investment to do so. But I will talk a bit about that in I guess, a few slides. So impact summary. By rewriting functions into this kind of Hamilton paradigm, they always, the Fed team gained naturally testable code, naturally documentable code, and data flow visualization for free, faster debug cycles, a better onboarding collaboration experience, and then this kind of central feature definition as a byproduct. So in total, that's why this was a home run. Cool. And then I actually want to claim here that by using Hamilton, the Fed team can continue to scale their code base and team without impacting their team productivity. So rhetorical question for you all, is that true of your feature code base? Could you just add to it and scale it without impacting your productivity? Okay, so what can you do with Hamilton? So technically, I would talk about three things. So one is, you can use it within any ETL system, as I alluded to before. You can scale it to big data and like parallelize it, and then you can kind of model any data flow, not just pandas. So you basically just need an ETL system that can run Python 3.6 and above. So Airflow, Metaflow, Dagster, Prefect, Kubeflow, like pipelines, they're all compatible. In terms of the recipe that you'd use is like you'd write your functions, you write some driver code, you'd publish your functions to a package or import it via other means, like, check using a repository. You'd include, SF Hamilton as a Python dependency, and then you'd have your ETL system execute this driver code, and then, you'd profit from that. And then, as I said, Hamilton grew up, working with data only fits on a single box, but Hamilton actually enables you to scale to big data. So Hamilton comes out of the box with the following integrations for Dask, Ray, and Pandas on Spark with minimum version 3.2. We're working on providing modem support. There is some modem support already, but just making it first class is something that's coming soon. The cool thing here is that you only really need to change the driver code to kind of make use of this, and so it makes it kind of easy to switch back in. So if you want to switch between Dask and Pandas on Spark, like Hamilton actually gives you a pretty easy way to do so. What I mean by that is, especially if we're talking about Pandas here for a second, the goal is to here are this logic I have here, and I don't want to change it to be able to run it on Dask or Spark. With Hamilton, you only have to kind of modify this driver script. So you need to like, change how data is loaded for the appropriate system. We have a notion of a graph adapter to kind of adapt the graph to make it run on a different place. And then it's just a matter of, creating the driver, requesting the columns, and then outputting things. And so this is, very minimal amount of code to get, your Hamilton Pandas code to scale. And the reason why this works is because Dask and Pandas on Spark both implement the Pandas API underneath. So you shouldn't, as long as you are only using a subset of Pandas that operates on those frameworks, you don't have to change your code. And then Hamilton allows you to model any data flow. So Pandas, check. Scikit-learn models, check. You can do that. NumPy matrices, yep. The IBIS project. Pretty sure it works. Essentially, any custom Python object, like you could kind of model with Hamilton. And so what Hamilton provides you is kind of lineage insights for free, since we can build this visualization. We have an ability that you can attach tags to functions, so you can attach a little more metadata and then query your DAG graph about it, and so you can ask meta questions. Would love contributions here. So, for using some of these things, you have to write, some of the code yourself. So would love, some contributions back to the project if you, are using NumPy and, have built something that you think would, help other people to use NumPy and, Hamilton. Also, would love to know, or feature requests, like if you're asking metadata questions about your graph, like what are they? How can we kind of help you, reduce the amount of code you write to kind of answer those questions? In terms of a common pattern that you use Hamilton is that you end up doing is that you end up kind of writing, a data loading module that you can kind of swap out, like Dask versus local versus Spark, and then you have your transform kind of modules. You then, you have one kind of driver code that runs in your ETL step. Maybe you have another script that's more for plotting or debugging that you either use in a notebook or is not in your ETL, and then. So you write your Python functions, write this driver code, and then in that driver code script, you would then save a data or an artifact. Once you get to kind of advanced uses of Hamilton is like if you need to do group bys, like there's several ways to kind of to model that in Hamilton. Maybe you write specific modules for it, and then maybe you want several things materialized along the way. Maybe then you start to kind of chain driver code. So you have a one Uber Hamilton DAG, and then you instantiate several Hamilton drivers that then compute or chunk the graph so you can save the right artifacts at the right time. Cool. So hopefully that made some sense and gave you a sense of like what you could do with Hamilton. In terms of future roadmap, one of the big things that we're looking to release pretty soon is data quality. Like most of the problems in production that people have, if it's not the code, it's the data, right? And so we think with Hamilton, actually the function and the way that you define a function, a very natural place to kind of, put some sort of kind of constraints or some sort of checks would actually be with the function itself. So here I have two mock kind of API examples potentially that we're looking at. as to like, how can we do a runtime check of your data to make sure that it conforms to your expectations. And the way we'd do it is like, you'd write your function, but then also annotate it with some sort of function. Now, for those of you who don't know, Pandera is one kind of open source library that does it. So we're looking at, how can we integrate, a Pandera schema to help do this, or maybe we'll do something very plain and simple ourselves. So we're still trying to figure out the API there, but that's something, we're looking forward to dropping in the next month or so. For those of you doing, want speed and maybe using GPUs or using NumPy directly, there are projects like Number, which can make your NumPy, code run much faster. With Hamilton, it'd actually be pretty easy to kind of, given a Hamilton DAG that's defined, say, well, in NumPy, get it to run with Number without you having to, go back and annotate your code. And so this would then allow you to kind of scale your NumPy and simple Python code to GPUs, and and you have C, Fortran-like speeds. We want to, our future roadmaps is still pretty open. We want to, respond to feedback and feature requests. So if you have ideas or issues, we'd love to hear them. Best way to do that is to come chat with us on our Discord channel, on our file issues on GitHub. And, if you have use cases of how you're using Hamilton, we'd love to know them too, so that we can, ensure that we're designing APIs and things to kind of, help you fulfill that use case. As I said before, we have support for Dask, Ray, and kind of Spark. But ideally, I want to graduate that support from being something that's a little experimental to something a little more we can kind of guarantee that the APIs are going to be more stable. So we'd love for people to try that part out, hear what works, what doesn't work, what documentation needs to be improved, etc. So we'd love some sort of thumbs up, thumbs down on these things, so we can graduate this support. We have, this is only just the quick highlights of the future roadmap. So we have a few more issues. Feel free to browse. If you like something, feel free to, heart it or thumbs up it, so that, can give us a little bit of signal on what we should prioritize. And so to kind of wrap things up, with Hamilton, you kind of write these declarative functions, right? And this is what I mean when I say it's a new paradigm to describe data flows, because you're writing these very specific functions. It grew out of a need to tame a feature code base at Stitchfix. I'm pretty sure it'll make your code base better too. And then by using the Hamilton paradigm, you can provide teams with, it provides model productivity improvements and scales with code bases. Thanks for listening. We're a nascent, open source project. We love your feedback. Please install us. If you like it, star us on GitHub. If you have issues, look at issues, vote on them. And then if you're interested in joining the community, feel free to join us on Discord. Thank you.
Great, thanks. Thanks, Stephen, for the great presentation. And I see we have quite a few questions we can go over right now. And just a remind, if you have questions, feel free to post in the chat. Or if you prefer, you can raise your hand. I can unmute you to speak, to ask questions, or even have discussions, follow-up questions too.
Yeah, so I think I answered most of the questions that I could. So I'm seeing a new one. Okay, so there's one for you, Bill. Could you send me the recorded? Yeah, Bill will send out an email of the recording if you're registered. In terms of another question, is Hamilton on CondaForge? No, it's not. If that's something that's required, do make an issue for it on GitHub, and then we can ensure we also publish it there. But otherwise, it's on PyPy. Yeah. I want to say good questions, everyone. They were pretty good. So the modem support is, so you can use modem support right now. If you wanted to use Hamilton, you would just, instead of importing pandas in your function, Hamilton function module, you would just import modem. But we're trying to make it so that you could kind of swap backends pretty easily. And so in which case we're looking to like make something in the driver script where you say use modin or not, so you don't have to go back and change your function modules if you do or do not want to use modin. We kind of want to use that option. So so in terms of helping there, we just need to figure out how to encapsulate changing your system modules paths to kind of a bit like Python mock test. You change where something points to. That's the kind of approach we want to do. So Richard, happy to I guess speak to you I guess on Discord if you're interested, but otherwise that's the kind of where we're at. And so yeah, if you have time, would love to get help if possible. But can you make a Docker image available for the user community to play around with the examples in GitHub? That's a good request, Krishna Kumar. Yeah, I think that's possible. I think actually we, with the new PyScript and kind of announcements from PyCon the other week, we might be even able to just make it available in the browser. But thanks. I'll note that as an issue to kind of see how we can fulfill for you. Thanks. Next question: is Hamilton used by data scientists in exploration stages? So the point of kind of Hamilton in some sense is to make the step from going from building something to production really easy and quick without you having to do much. So you can use Hamilton in a notebook. So I have links on towards just a data science post on how you can use Hamilton with a notebook. But in terms of from my experience, if you want your code to live long, it's always best to start, best practices from the beginning, in which case, yes, using Hamilton in exploration stages might be a little bit of a tax, but after that, from the tax you gain, you build up this module, this library of modules that then you can reuse for other exploration stages without having to reinvent the wheel. So so would love a random person in India to you play around with it and give us feedback. If Hamilton really sucks for exploration, feel free to create an issue and tell us why, what was slowing you down in exploration, and so maybe we can figure out a way to make things faster, right? Like caching or something. Next question: what were some of the challenges when making Hamilton? I think so. Hamilton kind of requires you to kind of migrate to. You can't be a swap and replacement. So really, the big lift is kind of figuring out because the slight paradigm shift. You have to think things slightly differently. Like Hamilton, especially if you're creating data frames, forces you to think in a columnar fashion, like compute your things in columns versus compute your things in rows. So other than switching that mindset and having to do some grunt work to migrate things, that was probably the most challenging stuff with Hamilton. But there are ways that you can ease the pain of migration by doing integration tests and a few other things and trying to make sure that things map in production. But yeah, I want to say from the code perspective, there wasn't too many challenges there. The main challenge I think is getting over the hump to adopt it and the mindset of how do you use Hamilton. Yeah, the nice benefit of columnar thinking is that you can generally that's also faster than row-based computation. So Hamilton might even help speed up some of your your transforms.
All right. Any last minute questions?
Yeah.